Okay, awesome. Today is going to be a lot shorter. We had the introduction to two courses, so that took a lot of time, just like default stuff, and also things I already covered. So today is not going to be too long. Okay, so let's start. First thing is linear algebra. And we are going to go on 4.3, which is linearly independent sets and then bases. So let's start with linearly independence. What does it mean to be linearly independent? Right, if I have, for example, if I have this coordinate system here, right? And I took some vector, this guy was my vector, and I took some other vector here, right? This guy. And these are my two vectors, right? Now, there is no way I can get back to the origin without adding vectors that are dependent on these two, right? I can't just go back to here. I can't scale this guy over there, right? If I do the opposite of him, right, he would have just gone there. But then I have to remove this guy, because if I kept them both, that means that I have another vector that depends on another, which means that they are dependent, right? So if I took that same vector like that and I drew it the opposite way, that guy would be dependent on that last guy, right? And we can start to see the mathematical definition soon. I'm going to show you. So let's draw a vector that's dependent on these two. So this vector here. And this brings us back to the origin, right? But without that vector, we couldn't get back to the origin. Okay, so the conclusion we have is that if we have C1, I'm going to use the same notation they used V, right? So V1, and that's our vector. And we created some linear combination here of all our available vectors. So C1, V1, up to C, they did P, so we can just write P, V of P, and that's equal to the 0 vector. So if this equation here only has the trivial solution, meaning that C1 is equal to 0, and all of these CP and all of these constants are equal to 0, then we have linearly independence, which means that we can't get back to the origin, right? That is what it means. If we had some other vectors that could make us go back to the origin, that would be dependence, right? You could also say it's the most unique vector, so I can't represent any other vectors from the set of these vectors. So what I mean is, like, if this was my set, I had 2 and 0, and then the other vector I will have would be, for example, 0 and 3. These are independent, right? I can't scale to 0 to anything to get 0, 3. But let's say I had, for example, 4 and 6 here. Now, if I added a C in front of here, 2, of course, I could add these two guys together and scale that by 2, and then I would have that last vector. So this set has a vector here that's dependent on these two guys. And you can also see very clearly what we are going to also tackle, that these two would form a basis. This and this vector will form a basis, right? Because they're independent, that's why. They're the most efficient way of spanning a subset or set or a subspace, I mean, of course. That is what it is. So these two will, of course, span R2, as you can see very clearly here. But if I had this guy, he isn't doing anything, right? He isn't adding anything. And then all of these three, that space there, the spanning, if I had the span here, that would not be the most efficient way. So we don't say that this is the basis, but if I remove this guy, then the set here, if I did a span on this set here, that will be the most efficient way, meaning that these two, meaning that these two guys are a basis, right? A basis for R2 in this case. Okay, yes, you can also see some other consequences of this. For example, if we have a single vector, if we have a set of a single vector, that vector was v1, and that single vector, let's say it was equal to 0, you could see that this, of course, is now linearly dependent, meaning that this right here is dependent, right? Because if I form other vectors from it, I still get the same thing, right? The dependent. I need the constants to be 0, but in this case, our vector was 0. So it's dependent, right? Which meaning that if this guy wasn't equal to 0, then it would be independent. Okay. Yes. Yeah. I've done that. And also we can use this abstraction here. We could use it for functions. So for example, dependence. So a set, like I said here, is dependent, blah, blah, blah. And also there's a theorem. What they actually just say is that very much what we have said, but I can state it, is that if you have some v1 here, and the first vector is not 0, right? And then you go up to some vj there, and of course you go up to some, I don't know, v of p, like that. Yes, then you can state if, let's say, if v of j can be expressed in terms of let's say C1, some combination here, C1, C1, V1, of course, plus up to, of course, C of j minus 1, and of course V of j minus 1. If the preceding vectors, right, if we can represent v of j by the preceding vectors, and that first one is of course not equal to 0, then of course we have dependence, right? That is what we mean. There's just a little bit more mathematically, right? Okay. And again, we can use this abstraction for functions. This is actually a theorem, but it's better to understand what it means. So let's use this abstraction then. For example, if I had, let's say I had a function p1, which was equal to t squared, and then I had p2, which was just equal to, let's say, 2t, and then I had p3, which was equal to 4t minus t squared. Then I could see here that if I did 2 times p2 minus p1, I have p3, meaning dependence, right? So no independence. So the set p1, p2, p3 wouldn't form a basis, of course, and in this set we would have dependence, right? Not be independent. Okay. I could be even more clear and see the spanning of this set, but yeah, you get what I'm trying to say. Okay. So the next thing here is basis. What does it mean? I already said some words on it, right? So we can just move on the meaning, and on a simple example I already show that. So we can just show some easy examples. So an invertible matrix is independent. Why? If you look at an invertible matrix, it has something special. If we have this guy equal to b like that, and if it's independent, of course, or if it's invertible, I have a minus 1, then x like that, then I have, of course, and I can do this, then I of course have a minus 1, and then B. That's the identity matrix, so I just have X equal to A minus 1 and B, like that. Okay, so this means, you know from invertible matrices, is that they only have a unique solution. And as well as we know, a unique solution here would, of course, form a basis. Now, why is that? Because we want the most efficient way of course, spanning a space. And if it only has one solution, that has to be, right? If I have, like I said, if I have, like I said, 2, 0, it's so easy to just do that. 0 and 3, I have these two vectors here, right? Would that make sense? Let's see. Would that make sense? An invertible matrix. Yeah. I asked that question there, right? The invertible matrix is independent. That means it only has one solution, and that solution is unique. That is true, right? But our question isn't actually B. Our question is actually the null space then. Yeah, because that's the question we're asking. Yeah, I am actually going to tackle this later, but I think you can apply the same thing here. Okay, we are not looking for B in our case. So this has only one unique solution. And we wrote it as B, but in our case, it's 0, right? So 0 and 0, meaning that the only way we can get this is if we have constants in front of here, right? This is only possible if those constants are 0, right? Otherwise, I can't do that. I think that should be correct. That's my idea. Okay, we'll stick with that for now. I'm going to do some tasks tomorrow, I think, so I can try this out. Okay. Yeah. And of course, the unit vectors, those bases, so in R2, we call those the standard bases, right? Okay. Okay, next we have is the spanning set theorem. It actually just is pretty easy. What it just says is that if you have, let's say, like earlier, if you have some space and you want to find, or you want to find the basis for that space, or not, you don't want to find basis for it, but you want to create, you want to make that space as efficient as possible. You of course remove those dependent vectors if you still keep the space. Oh, that wasn't good. Okay, so I'm trying to say is that, let's say you had this space here. You had this span here. This span, let's say you said h was equal to the span of this vector, this vector, this vector, right, etc. So we have this. Then, if I can remove some vectors from my space h in this case, and it's still h, right? If I can keep on doing that until it's not h anymore, right? If I can keep doing that until I hit that, what you would say, limit, then I of course would develop the basis for h, right? So if I, let's say I call you v1, I call you v2, and I call you v3, and I call you v4. If I first remove v4, right, I remove v4, then we still, as you can clearly see, we still have h, right? This is still the same space. Nothing has changed. And now if I remove v3, then v1, and then v2, I still have the same space, but now I can't remove. If I remove v1 or v2, I wouldn't have the same space, right? That is what it means, okay? So we can just remove, and you see it clearly, right? Usually what you do is actually row reduction. You can do that as well. But I think we're going to do that in call A. Yeah, I'm pretty sure we're going to do that call A. Yeah, but usually here you can see it. Okay, but we are going to do that when we have call the span of call A, right? Okay, which we actually have here. So yeah, but we get back to it. Okay, the next one is the basis for null A, but I kind of showed it here with that invertible matrix idea. So let's just skip that and go to that call A. And this one is pretty simple, right? Like I said, you could very clearly see what will form a basis, right, for call A. And actually, what matters, if we have made this into a matrix, you would see that only the pivots are the ones that are bases, right? And why is that? So if I had some matrix here, like I had 0, well, let's say we need 0, and then I had 2, 1, 0, 0, 0, and of course 1 there, and I had 2, let's say I had 0. Let's say this was my matrix. Now only the pivots here would form. Let's change this. Let's go one step further. That will be much more interesting. 0, 0, and 0. Yeah, like that. This would be even better. But no, that wouldn't be good either. I should actually do that the other way. That would be even much more interesting. Right, so if I did this, and I did 0 there, and 5, and 2, just to, yeah, have fun. Okay, now, here is a better example. So, this one, of course, can represent v1, and v2, and v3, and then v4, and of course the span of these guys, right? The span of these guys represent a space, right? But not all of them are a basis. Actually, only these 3 are a basis. And why are only these 3 a basis? The reason is that they have pivots. This guy does not have a pivot. And why pivot then? Because if it's not a pivot, which means that it isn't bound to a dimension, and also when it's pivot, it's only one unique solution, which is what we need in order to have linearly independence. But if we not have a pivot column there, right, that means we either have infinite solutions or we have no solution. So we need a pivot in order to have linearly independence, right? Okay. So, and I'm not going to do that row echelon. That is from the because also we have if it turns out that let's say this A here, let's say we call this A. Let's say this is A, and we have another vector B that can be row reduced to A, but B is more complicated. It isn't row reduced, but it can't be row reduced to A. Then the same thing applies for B, right? And the reason is because row reduction can't change linear dependence, the linear relationship between our system of equations. That is what row reduction can't change, right? We are just doing linear operations on each row, so that shouldn't be changed. And it's easier to see with an example, so I can show what I mean. If I had, let's say, 2, 0 here, and I had, let's say I had something like, let's say we had 2, 1, like that, and then I had 4 and 2, and then I had, let's say we had something like 10 and 14, just to make it fun. Okay, if I now row reduced, and I took, let's say I wanted to get rid of the one on the top, so I took -2, 0, -2, 0, -2, that's 28, and that's of course 28. What are you talking about? -2, yeah, that's 28. And then of course 10, that's -18. So -18. Then I have 1, 2, and 14, right? Okay. So now, if I tried, let's say you can clearly see here that, for example, this is let's say this is V1 and this is V2. If I did 2 times V1, I get, of course, V2. Okay, let's try this on this side too. If I here did 2 times 0, that's 0, and 2 times 1, that's 2. So that's still true, as you see. So the relationship in terms of row echelon form is just the same here. But what isn't the same is the column space. And you can actually see that if I now managed to this guy 18, I can get rid of him. That's actually possible. If I get rid of him, we are not covering one whole, you see that the whole X is just gone then. We are not spanning X at all. But this guy is of course expanding both X and Y, right? So if you row reduce, you can't change the column space, right? Okay. Yeah, that was actually it. The plan was to show that row echelon form from the book, but I already did some simple examples, so that works. Okay, tomorrow I have a full day, so that one will be much longer. Okay, see you tomorrow.